Okay, so today we're going to be looking at the Bronsted-Lowry theory of acids and bases. Now, you've obviously met acids and bases before. You've used them in a range of different reactions throughout your time at school. But what we want to do today is talk about the theory that allows us to really understand what's happening at a molecular level for a substance that's acting as either an acid or a base. Um, and it gives us a bit of insight into these reactions and exactly what's going on there. So first of all, we've got our questions. Read through those, get them in your mind so you kind of know the direction that we're going. And yeah, so first of all, acids and bases then. So we understand the different reactions that acids and bases both undergo. We know acid-base reactions when you react them both together um, as neutralization reactions. But really what we need to do is actually explain what's happening at a molecular level um, for an acid and a base. So that's where we use Bronsted-Lowry theory, which is essentially that an acid is described as a hydrogen ion donor, and a base is described as a hydrogen ion acceptor. Okay, and that's really sort of the basis of what's happening. Okay, that we just describe any acid using Bronsted-Lowry theory. Any acid is something that can donate a hydrogen ion, okay, to another species, and a base is something that can accept a hydrogen ion from another species. So we've got that. Now, the next thing then is to talk about the actual transfer of that. So we've said that a acid will donate a hydrogen ion and a base will accept it. So therefore there must be some sort of hydrogen ion transfer. From now on, I'm just going to call a hydrogen ion a proton, since a hydrogen is a proton and an electron. So a hydrogen ion, a positive hydrogen ion is just a proton. So I'm going to refer to it now as a proton. So you can say an acid is a proton donor, a base is a proton acceptor. Okay, so what I would like you to do is identify the acid and the base in that following reaction. So looking at that reaction, which species is the acid and which is going to be the base? So have a think about that. Just jot down the reaction and just, write down what you think, and we'll go through it. Okay, so it should have been quite clear that obviously HCl is the acid in this case. It's we know hydrogen chloride acts as an acid. When dissolved in water, it forms hydrochloric acid. So here in this case, we've got the hydrogen chloride donating a proton. Okay, so we can see it here donates a proton to the ammonia, which is acting as a base. Okay, it's got a lone pair of electrons which it can accept a proton with, and we form this ammonium. Okay, so the NH4 positive and the Cl minus, which is the chloride. So it's ammonium chloride. Okay, and that's a solid. So I know I've separated it into the two ions, but that's just for clarity to see that the hydrogen chloride has definitely given up its hydrogen, and the ammonia has accepted it. So we've got ammonium chloride. So that's just, a very simple case there. Now we need to discuss the oxonium ion because we've used it. We use it without even thinking about it. Whenever we describe an acid, we are actually describing the presence of oxonium ions. So whenever an acidic substance, so HCl as an example, is dissolved in water, it will donate a proton to the water. So the hydrogen chloride is the acid. It's donating a proton to the water, which is acting as a base because it's accepting that proton, and it forms this oxonium ion, okay, which is H3O plus, and also the Cl minus. Okay, so you can see that the HCl has donated a proton because it's lost it, and the H2O has accepted the proton. So can you write down all the species there that are acidic and all of the species there that are basic? Okay, so from what I was saying, hopefully you caught on to the fact that obviously the HCl is acting as the acid and the H2O is acting as the base. But what you also should have seen is that the H3O plus, okay, could also act as an acid. Right? It's got hydrogen that it can donate, and the Cl minus can act as a base because it can pick up that hydrogen again. So essentially, this reaction can go backwards, and we can form this and this from these two. Yeah, it isn't likely to happen. HCl is such a strong acid that it will donate its proton, and the Cl is very, very, very unlikely to pick that hydrogen back up. So with strong acids, this is almost certainly going to go in this forward direction, and it's very, very, very unlikely that the Cl will actually pick that hydrogen back up. And just another note, we often simplify the H3O ion, the oxonium ion, just to H plus. We don't need to keep writing out H3O plus each time. H plus is sufficient there. And another thing that we've probably, you've come across quite a lot is the terms bases and alkalis. Now, um, it's important here to distinguish between the two. So a base is any substance which can accept a proton, yeah, a hydrogen ion. And an alkali falls under that umbrella, okay, it falls within that, but it also forms OH minus ions in solution. So essentially, an alkali is a soluble base. If you dissolve a base in water, it will form OH minus ions, okay, and that's what an alkali is. Whereas a base is just generally any substance which can accept a hydrogen ion. Okay, so if we have a look at this example here, we have a carbonate ion reacting with water to form HCO3 minus, okay, and OH minus. And what that tells us is that the carbonate ion is acting as an alkali. It's forming OH minus ions in solution. It's a base because we know it's accepting a proton, and it's an alkali. Okay, so it's like the subdivision of the base. Being a bit more specific, it's an alkali because it forms an OH minus ion in solution. Okay, so what I'd like you to do is just like before, determine which of these species is acidic and which ones are basic. Okay, so which ones are proton donors and which ones are proton acceptors. Okay, so we're going to be a bit more specific now and add a few more sort of terms into our glossary. So we have acid and base, right? So we know that the carbonate ion's a base because it's accepting a proton, and we know that the H2O is acting as an acid because it's donating a proton. But now we've also got this conjugate acid. So we know it's an acid, it can act as an acid because it's got this hydrogen that it can donate going back in this direction. And we know that this OH minus is a conjugate base because it can accept a proton and go back in this direction. Okay. The reason we say conjugate acid and conjugate base is because they pair up. Okay. So for every base we have a conjugate acid, and for every acid we have a conjugate base. So if we look at the carbonate ion, which is our base, that accepts a proton to form this HCO3 minus, which is our conjugate acid. Okay. It can, in theory, donate this proton like an acid, yeah, acting as an acid, and go back in this direction. So moving over to the left. And similarly, if we have our H2O, which is acting as our acid, it's donating a proton, we also have this conjugate base. Okay, the OH minus can, in theory, pick up a hydrogen ion and go back in the direction towards the left-hand side. Yeah. So for every base, we have a conjugate acid, and for every acid, we have a conjugate base. And the strength of those conjugate acids and conjugate bases is dependent on the acid and base that they were made from. What I mean by that is, if we had a very strong acid, we'd have a very, very weak conjugate base. So that conjugate base isn't very likely to pick up a proton and go back. And if we had a very strong base, then we'd have a very weak conjugate acid. Okay, so that conjugate acid would be very unlikely to donate its proton and go back to the left-hand side. So strong acid, weak conjugate base, strong base, weak conjugate acid. So acid-base pairs is what we call them. Okay, so it's conjugate acid-base pairs, and we'd always have the acid and its conjugate base, okay, and the base and its conjugate acid. So what I'd like you to do is, looking in your ideas book, page 181, there's a table of conjugate acid-base pairs. I'd like you to look through them and tell me what's interesting about water. Okay, so write down what's strange, anything that you can see that seems to be a bit weird. Look through that table and tell me anything that you find a little bit odd about water. Okay, so hopefully it was clear that water can actually act as an acid or a base. Okay, it's basically a substance that's amphoteric. Okay, and it can act as an acid or a base. So in this first case, we've got H3O, so the oxonium ion, donating a proton. Okay, so we've got water here essentially acting as a base. It's going to pick up this hydrogen ion and form the oxonium. And here we've got the water, the H2O, acting as an acid. It's donating a hydrogen ion to form H plus and OH minus. So water is very interesting in the fact that it can act as an acid or a base depending on what else it's reacting with. So if it's reacting with a strong acid, it will act as a base. If it's reacting with a strong base, it will act as an acid. So it's kind of a middle ground. It can act as both acid or a base. Okay, and that's called amphoteric. Okay, another thing then. It's important to note that unlike in redox reactions where we know oxidation states will change, okay, so in displacement reactions when one thing replaces another and we get oxidation state changes, With acid-base reactions, there is no change in oxidation states. Okay, so you can actually see here the hydrogen has got an oxidation state of +1, +1, +1 all the way through. Cl's got a charge of -1, -1 all the way through. Sodium +1, still +1, and the oxygen -2 and -2. So you can see the oxidation states do not change in an acid-base reaction, and that's just worth noting when trying to determine between an acid-base reaction or a redox reaction. A acid-base reaction, the oxidation state will not change for anything. Right, so just a little bit of practice then. So 3 reactions. Which of those reagents are the acid and which are the base? And then you can also tell me which are the conjugate acid and conjugate base as well. So which is the acid, which is the base for those 3, and then as well, if you can, which is the conjugate acid and which is the conjugate base. Okay, so I've color coordinated them then. So we've got NH3 being the base, okay, because it's picking up a proton, and the HBr acting as the acid because it's donating the proton. Then we've got the ethanoic acid here acting as the acid because it's donating a proton, and the water acting as a base, it's accepting a proton. The sulfate ion and the oxonium ion. So the sulfate ion is acting as a base here, it's picking up a proton, and the oxonium ion is acting as an acid, it's donating a proton. And if we look here, we've got the NH4, that would be the conjugate acid of NH3, and Br- would be the conjugate base of HBr. The ethanoate ion here would be the conjugate base of the ethanoic acid, and the oxonium ion would be the conjugate acid of the H2O. Then we've got the HSO4, which would be the conjugate acid of the SO42-, and then H2O, which is the conjugate base of the oxonium ion. So here we can see, just in this example, we've also got water acting as a base and as an acid. So I think I mentioned this before, but it's worth noting that strong acids have very weak conjugate bases and strong bases have very weak conjugate acids. Okay, so what that means is if HCl dissociates in water, so it forms, it donates its proton, the Cl- is very, very, very unlikely to pick that hydrogen ion back up and act as a base. And in the same sense, the NaOH is very, very, very unlikely to, when it, accepts its hydrogen ion, forms H2O, it's very unlikely for that sodium ion to then pick back up the OH, yeah, and go back in the other direction. So strong acids have weak conjugate bases, and strong bases have weak conjugate acids. So hopefully you can answer those questions. Went through it quite quickly, but hopefully that was clear. Answer the questions and then we'll check them. Okay, so how do we describe acids and bases? Well, acids are proton donors and bases are proton acceptors. What's the difference between a base and an alkali? Well, a base is a proton acceptor and alkali is a soluble base. Okay, so what that means is it forms OH- ions in solution. Can you identify conjugate acid-base pairs? Well, just be aware that for every acid, there will be a conjugate base for that acid, and for every base, there will be a conjugate acid. But the relative strength of those conjugate acids and conjugate bases depends on the original acid or base. What is the oxonium ion and how is it formed? Well, it's H3O+ and it's formed when an acid is dissolved in water. Yeah, it donates a proton to water and we form that H3O+. So hopefully that was clear. You'll be going through some problems and things in class hopefully with this, and yeah, so good luck and I will see you next time.